thing?
range.
Okay.
I mean, there's something later that you'll run into called the range formula. That is, if I shoot an object into the air, how far will it go if it lands at the same height from which it was shot? That's called the range formula. So if I just generalize it, range is just how far it goes. So, would you have a questioning look on your face?
I put on my calculator and I got 0.48, and I'm just like, did I multiply?
You got 0.48, what,
No,
here?
no, for the, like, it's 0.96, but for some reason I got 0.48.
Oh,
I don't know.
and possibly now this was rounded. That if you did 0.1 versus 0.09, that might be the difference.
I just put in, like, I was right there.
All right, and versus, I guess,
Yeah, you're probably right, or.
you did
that
0.1?
I put whatever answer I took from the original equation.
Okay, you didn't round.
Mhm.
Okay. Yeah, on a quiz or test, I'm not worried about that at all. All right, so let's try the negative. Let's see what did we get. So if my initial velocity, so it's being thrown downwards, so my initial velocity is negative,
89.86.
thank you, 0.86, this is my initial velocity. Plug it into, I guess, the same equation over there, so I have negative 90 equals negative 89.86 minus 0.62 t.
Wait, aren't we doing positive this time?
No, no, we're doing it. The time is 0.225 seconds, or 226, go ahead.
Negative.
Yeah, wait, no.
It'd be convenient if it were negative, but like,
No, it's positive.
I got it.
it's a positive answer. Why would it be convenient if we've gotten a negative time?
So
We know it's not correct.
All right, so we have time is 0.226 seconds, and so we need to figure out what is the initial velocity, so, oh wait, no, we have that. We're trying to figure out, range. So R is equal to 72 times 0.226.
72 times that big number.
16.26 meters.
So we have one being thrown downwards and the other one being thrown upwards. And first off, if you're throwing a particular, well, no, you have two different ranges there. I'm thinking they're both valid answers. There are two answers to this. If we use that equation, we
Yeah,
use this equation.
That makes sense. Cause we don't know that.
Pardon?
That makes sense, cause we don't know that.
I'm wondering if the first one. Can we use it at all? Oh, we don't know if we, so let me talk about, actually, the way that I had approached this was a little bit different, so I wanna go into that. Any questions on what we've done so far before I tackle it a different way? All right, so what I'm gonna do is I'm gonna combine these two equations right here. The first and the third one as they're written. And I need some space. So from the third equation over there, I know that VI is equal to VF minus AT. If I plug that into the first equation, I get delta S is equal to VF minus AT times time plus 1/2 AT squared, which is VFT minus AT squared plus 1/2 AT squared. So I end up with delta S is equal to VFT minus 1/2 AT squared. This is the fifth equation that some textbooks will give. If we solve for time in that, let's see what we get. If both the original problem, if both of our solutions are valid, then we should get, well, our two answers of 290.09 and 0.226. So plugging into that equation, I got negative 20 equals negative 90t minus, actually, the plus 1/2 0.62, let's minus and minus t squared. So I end up with 0 equals 0.31 t squared minus 90t plus 20. T is equal to 90 plus or minus the square root of 90 squared minus 4 times 0.31 times 20 divided by 2a to 0.62. And we will end up with two answers, two positive answers.
seconds.
So far, so good.
And then 0.222 seconds.
And we had 0.226. Yeah, we had 0.226 versus 0.222, and then 20.10. Or two, wait. I think
I got 290 for the, when you put plus.
I think my brain just flipped it. All right, two answers. So they actually answered the question. Oh, actually, the question was that, so we have our two answers. I was thinking that the initial velocity would be 72 meters per second I hat plus 89.9686 meters per second J hat, and 72 meters per second I hat minus 89.86 meters per second J hat. And for those that like polar form, then do the trick. Personally, I don't like problems, and this is one of the reasons, with this being so small, these got really close to each other in magnitude, which, you know, depending on how you round it, you can come up with some very different answers when they're that close.
Oh, I get what you meant. Because if it would have had like Earth gravity, our numbers would be close together, but it'd be an obvious answer, you know?
Yeah.
Like 16 point whatever, or something. Meanwhile, here it's times 0.222. Somebody could put 226 and that's the difference, but we don't really know.
Or if you rounded off the first one to 89.9, then that could, you know, you'll end up with
Okay.
0.4 something.
Yeah.
I don't know what it would be, but
But yeah, I get what you mean.
All right, questions, because on projectile motion, because I'm not planning to move on past it.
So, when we have questions in the second format where the angle is unidentified, are you gonna say like, oh, the ball is thrown upwards or downwards, or are you gonna say, give me both answers?
It can be both answers. Typically, assuming I don't make you Carol's error when I'm working out the solution, I would say, what are the initial velocities? Give you a plural there to
Okay.
indicate that there's more than one answer. Or if there's more than one, just say, some problems I'll do, if there's more than one answer, just give me one of them.
Okay, perfect.
And sometimes there's a Carol's error on my part. That famed first year quiz where I gave them a problem that actually had no solution. And no one asked about it until most of the people handed it in and gone. And then someone said, oh, is this even possible? I said, sure. And then I looked again, I thought, wait a moment. And I worked it out. So I gave a re-quiz on it and made a mistake when I was working it out, and it still was unsolvable.
What did they do? They just,
It was one of those things where you end up with, I think there was one of those negatives under the radical, and too many of them just went, make it positive so we can work it out.
oh.
Make it dumb. Listen, I don't understand why people think you can do that, cause like, this guy kinda goes against like math.
Yeah, just, we have more boundary conditions here than in math class.
Yeah.
All right. Just a quick story, sort of reminiscent of when I threw the marker over here, and I did not hit Carly Ann. I was doing the next bit with a younger group, and I did not hit Scott, just so you know. I was closer to Scott than I intended, but I did not hit Scott. But last period, the student came in and said, Dr. Fox, I heard you hit Scott this morning. Did not hit Scott. Scott was prone to exaggeration. His mom knew. Like, I was still waiting for that phone call from a parent going, I heard you hit my child. I did not. The first year I was doing the centrifugal motion lab, I didn't have the rubber stoppers yet, so we were using some of the slotted masses, those metal things, and the string broke, and this metal mass comes shooting across the room, smacks into the board. No one was hurt, thank goodness. But it's one of those moments where you're going, ooh, like Jose. All right. As I swing this around, the question is, when I let go, where will it go? So I'm going to swing it from here. No, I did not hit Scott. I want to hit the X.
Oh, okay.
So we'll draw up our really fancy diagram of the room. I'm standing here, and I'm going to swing it around, I guess from like this, in this direction. And the X is somewhere around there. So from a point of view of communicating, 12 o'clock, 3 o'clock, 6 o'clock, classic clock face. Where do I need to release it in order to hit the X?
I wanna say that you'd probably release it at like 1:30-ish, because it still
Two,
has.
I was gonna say 2 o'clock.
So somewhere, now in terms of my own potential, hand-eye coordination, I probably can't differentiate between 1:30 and 2, so those are
Yeah.
the same to me.
Yeah.
Anyone might have a different answer.
I was gonna say 3,
I
but
was gonna say 3 as well, but I don't know.
Felt good?
Oh, okay. 3 o'clock would be, like, if you dropped it right in front.
Release it here.
Yeah, so like, if you, straight on.
Yeah, so that's 3 o'clock, then 1:30 is at 2, somewhere,
Yeah.
that's sort of 1:30, 2 o'clock.
Well, I would say it'd have to be, well, after 3 technically, so like before 4 o'clock.
Over here?
Yeah. Cause since you're going like this, as you're coming in, that started those that spinning force, so you'd have to release a little sooner than 3 for it to go where you're trying to
Yeah.
make you go. If you dropped it right on 3, I would say it'd go to the left instead of just straight on. Just a little bit, but it wouldn't go straight forward.
Right. Anyone else? So basically 4, 3, and then 1:45.
It's at 2:30.
I appreciate your belief in my skills. All right, I'm gonna be swinging it up here. Yeah, just in case it slips. Charlie Ann and Zachary, if you could just sort of move back. I think you're safe, if you're feeling uncomfortable.
Am I safe? You know what? It's just gonna be a pleasant surprise.
All right, so 4 o'clock. So if that's 3 o'clock there, so 4 o'clock would be releasing it here. Now, ideally, I would swing it a lot faster, but I lose some of the control, so we'll go 3, 2, 1, release.
Oh. Not there. So, got it for you.
Down here.
Oh, I thought it go over there. My bad.
You did a pretty good
That whole
job.
rubber thing. All right, so 3 o'clock.
I was impressed.
She still has faith. Okay. 3, 2, 1.
Oh, that was
actually
close
really
here.
close.
That, now, we start getting into hand-eye coordination issues. So, that was released actually a little bit late. I'm gonna do this more slowly.
Oh, okay.
3, 2, 1. Still, it's catching on my hand.
No, so 3 o'clock is pretty close too. It's probably not 3 o'clock on the dot, but
That's 3:15.
like 3:15, yeah, or 3:30. Something like
It's more like 2:45. One more. Last time I'm gonna try it on this one. Good thing it's not being filmed. 3, 2. That was more like 3:15.
that. Okay.
It's over.
Dang, that thing really ran around.
And let's just go ahead and do the, somewhere around here. So we're releasing a little bit off. Apparently, I can't differentiate with an hour and a half. When I let go, which way will it go?
The direction that it had the tendency to go, I guess.
Bring it back to inertia. So if I am swinging it around like this, swinging in that direction, if I let go of it here, it should go straight. There, once I release it, what are the forces acting on it once I release it?
Gravity.
Would be better than that,
Wait,
okay?
That's it.
Air resistance.
We got those two things. No Jedi powers, there's no,
Yeah.
motion doesn't have any memory, and the fact that once I let go, it's not going, well, I was traveling in a circle and I'm a little bit dizzy right now, but it doesn't do that. So to hit a spot here, I would need to release it, you know, somewhere around there, not the scale of what I just did. But it does travel off at a tangent.
Oh, I get, okay.
Now, because the force of gravity was acting on it downwards, there was some bending down. That doesn't go in a line drive. So it has some velocity here, it has some velocity here. If I'm traveling at the same speed, did my velocity change?
No. If your velocity is not changing, your acceleration.
I said, my speed is not changing, does my velocity change?
Velocity's dependent on the direction, so I guess wherever you throw it, I guess your velocity changes.
Oh, so
Yeah.
it's changing constantly.
Yeah. Okay.
Because the acceleration we deal with in chapter 2 is about change in speed. We are now addressing, this is not, we'll get into this more detail in chapter 6, 7, one of those two. But there is acceleration just purely from changing direction. This acceleration is called centripetal acceleration. It is the acceleration because of a change in direction. So if you're going around a curve at a constant speed, yes, you're accelerating. So given this,
Oh.
if you are driving an automatic transmission,
All right. I'll stay.
what are the 3 accelerators that you have access to as a driver?
Well, regular, like, speed acceleration, because we can go, right?
You do. I'm not quite sure what that was.
I don't know.
You flying a plane?
Yeah.
But, you know, we got the throttle, we can change our acceleration at will.
Okay, the gas pedal, go translate to a car.
Yeah.
Okay, so we got gas pedal. That is an accelerator.
Brake pedal.
That's another one.
Cruise control.
Cruise control, not,
You
can change it in the steering wheel?
I guess.
okay, no cruise
No,
control.
but-
Simplifying it, all cars, not all cars have
Now
that.
we would also have centripetal acceleration, because we got our steering wheel. We can
Yes,
go and steer.
steering wheel is an accelerator. From a physics point of view. I suspect if you went to a car dealership and talked about the steering wheel as an accelerator, they'd look at you blankly. But I haven't tried it, I don't know.
You should try it.
Oh my god.
Now, this acceleration, looking at the roots here, this is center. This is seeking. PET is the root meaning seeking, but we do have other words in English that use that root to mean seeking.